So today is day 2 of section 10.1, which is really learning more about parametric equations. And we're going to add in the formula for surface area using parametric equations. Hopefully it'll all make sense. If not, make sure you ask questions when you come to class tomorrow. Okay, so we're going to start off with this first example that says to find the slope and the concavity of the curve x equals square root of t and y equals t squared minus 4 over 4. So we're going to start by taking the derivative of y and the derivative of x. So dy dt is equal to t over 2 and dx dt is equal to 1 over 2 times the square root of t. So therefore, dy dx, which I need in order to find the slope, is equal to t over 2 over 1 over 2 root t. With some simplification, that becomes t to the 3 halves. Okay, so you will want to do the algebra on your own, but t to the 3 halves. In order to find the slope of this, I need to substitute a value in for t, but I don't have a value for t. I have a value for x and a value for y. So I'm going to choose one of those two and substitute it into the appropriate parametric equation. So I'm going to take 2 and substitute it in for x. So I get 2 equals the square root of t. So at the time in question here, sorry, at the x value in question, the t value is 4. So now I take the 4 and I substitute it in over here. So I'm evaluating this at t equals 4. So the square root of 4 is 2, and 2 cubed is 8. So the slope at the point 2 comma 3 is 8. Okay, so now we're going to use our second derivative formula from yesterday. So we're going to let dy dt, kind of separate this stuff here. So we're going to let dy dt equal y prime. So y prime is actually equal to t to the 3 halves. And now I want dy prime over dt. And dy prime over dt is going to be equal to 3 halves t to the 1 half. And then remember to find the d squared y over dx squared, excuse me, is equal to the dy prime part, so 3 halves. I'm going to write that as the square root of t, over, then you take the dx part and you divide it by that, so that is 1 over 2 root t. And so when I simplify this whole thing out by multiplying by the reciprocal, I get 3t. And remember, we're still evaluating this at t equals 4. So the second derivative is equal to 12. Now we just have to remember what that means, going way back to earlier in the year. It's like a chapter 4 concept. So when the second derivative is positive, you know that the graph is concave up. All right, moving on. So this question says that you're supposed to convert the parametric equations from the previous slide into a rectangular equation. So that's something from last year. Hopefully you'll be able to figure that part out, but then you want to confirm it. So we actually want to find the first and the second derivative once we rewrite it. So I'm going to start by taking the x equals the square root of t, and I'm going to square both sides to get t alone. Then I'm going to take that t value and I am going to substitute it into the y equation. So y equals 1/4. And remember, this was, what was this? T squared. I can't even see it on my page here. T squared. So this is going to become x to the 4th when I square the square, minus 4. Or I believe I had it as one fraction. So this is really x to the 4th minus, let's write it like this, because that's what I need to work with anyways. X to the 4th over 4 minus 1. Okay, so now my first derivative with respect to x is just going to be x to the 3rd. And I want to evaluate this at an x value that I know. Well, we know that x was, remember, it was the 0.23. So x was equal to 2. So this gives me my derivative, or my slope. 2 cubed is 8. And then I can take the second derivative, and the second derivative is 3x squared. And again, this is still at x equals 2. I substitute 2 in there. I get 4 times 3 is 12. So there you go. We confirmed it. So we can see that the parametric equations actually work doing it that way. All right, so now we are going to talk about surface area of a smooth curve. So if a smooth curve, x equals f of t, y equals g of t, so x and y defined parametrically, when t is between some values a and b, is traversed, that just means travels or moves, exactly once as t increases from a to b, then the areas of the surfaces generated by revolving the curve about the coordinate axes are as follows. So if you're going to revolve this about the x-axis, then the surface area is equal to the integral from a to b, 2 pi. So now we're revolving around the x-axis, so this is going to be a y. So 2 pi y times the square root of dy dt squared plus dx dt squared dt. Hopefully you can take a guess that when you revolve it around the y-axis, then this will be again from a to b, but we're switching it out here. So 2 pi x and then the square root of, and you'll see most textbooks for some reason will switch and put dx dt squared first. Of course it doesn't matter, but it just seems to be the way it's written. That's a y, and then in terms of t. Okay, so obviously I can't give you a formula without doing some practice problems. So we're going to see, I'm going to use Desmos a little bit here. We're going to use our calculator at some point in time too. So I'm going to kind of show you how to think about it and how to determine when it's a calculator and non-calculator question. Okay, so here's the first problem. It says find the surface area generated by a circle of radius 1 whose center is at 0, 1. So here's the center at 0, 1. And it's revolved about the x-axis. So important to read that. So you can see that when we revolve this thing, the whole entire circle is going around the x-axis. It's going to make quite the strange shape. So I need to write this thing parametrically so I can actually come up with the integral. We're going to create this integral, right? So as a quick review, a couple of quick reviews, I'm first going to start off, hopefully by not having problems with my mouse. I don't know why it's doing that. Let me erase this, maybe. Okay, so I am going to write the equation of the circle centered at 0, 1. So this is the equation of the circle centered at 0, 1 with a radius of 1. So this is my equation of the circle, and that's what's graphed over here. And I'm going to rewrite this in terms of sine and cosine. So last year we took circles and we rewrote them parametrically by thinking of x being like your cosine. So if I let x equal cosine, oopsie, sorry, don't like that. X is going to be cosine of t. Hopefully this is going to sound familiar to you as we're doing this. Oh, I did it again, you guys. Don't want squared, I just want cosine. X equals cosine of t. And if I squared it, I'd have x squared and I have cosine squared. And that would be, I'm going to end up with cosine squared here and sine squared here. So that's what we're aiming for here. I am going to let y minus 1 equals sine, or if you want to think of y minus 1 quantity squared equals sine squared, I'm solving for y and I get this. Okay, and in my surface area formula, I need dx dt and I need dy dt. So dx dt is a negative sine of t, and dy dt is cosine of t. So now I'm going to use the formula to find the surface area, right? So this is going to be, I'm going to pull the 2 pi out front, the integral. And one of the things you want to be careful with is understanding how much of the graph we actually need to use. So since it's this whole entire circle, that I'm revolving, I need all of 0 to 2 pi. So I actually need the whole entire, well, the whole entire surface bounds. I'm having problems with my writing on the screen today. All right, so we're going to integrate from 0 to 2 pi. And then remember the formula is 2 pi, and then it's y or x, depending on what you're revolving around. So we're revolving around x, so this is going to have a y here. So this is 1 plus sine of t. And then it is the square root of, so it's going to be dy dt, which is cosine squared. And then dx dt squared, which is going to give me sine squared, which I hope you can tell by looking at this, that this is a really nice problem to do by hand, because this is all going to go away, right? This is just 1. So what I am integrating is 0 to 2 pi, 1 plus sine of t dt. Don't like it so big. Let's try that again. Oops. Come on. This is making me mad. Okay, so now 2 pi, the antiderivative of this is going to be t minus cosine of t from 0 to 2 pi. So 2 pi times 2 pi minus cosine of 2 pi is 1 minus 0 minus cosine of 0 is 1. So the 1's will cancel out, and I'm left with 2 pi times 2 pi, which is 4 pi squared. Perfectly fine to leave it just like that. Okay, next problem. I'm actually going to try and do an ugly sketch as opposed to using Desmos here. So we're going to create an arc of a circle. The circle is centered at the origin, and we want to figure out the length of the arc when you're going from the point 3, 0 to the point 3 halves and 3 root 3 over 2. So let me get the circle in the right spot here. That ought to do it. Okay. So the point 3, 0 is over here, radius of 3, 1, 2, 3, and the circle's going to go this way. And the point 3 halves and 3 root 3 over 2, you really want to think about where that is on the unit circle first. So this is really 3 times 1 half comma root 3 over 2. And the 1 half root 3 over 2 is going to be at, I'm letting you see if you remember, pi over 3. Okay, so pi over 3 is about here. So we're looking at, I don't know, now I put the point right where I want it to go, I guess. So we're looking at this arc length here. So that whole entire stretch of it, and we are going to revolve it about the x-axis. So you're going to have some stuff that's going to come down this way, okay? All right. Well, that was terrible. Okay, so now let's integrate this. Set it up, I guess. So I need to rewrite the x squared plus y squared equals 9 with the 1 on this side over here. So this becomes x over 3 squared plus y over 3 squared equals 1. And then just like we did on the last problem, I'm going to let x over 3 now equal cosine and y over 3 equal sine. So that means that x is actually equal to 3 cosine of t and y is equal to 3 sine of t. And that means that dx dt equals negative 3 cosine. Nope, that is not what it equals. It equals negative 3 sine of t, and dy dt equals 3 cosine of t. It tends to be that when you are working with a circle, you should be able to um, do the problem without a calculator. It should work out that you can get to the answer without a calculator. Okay. Let's see, what color do we want? That should be good. All right, so now my integral is 2 pi from 0 to pi over 3. And then because we're revolving around the x-axis, we want the y. So that was 3 sine. And then I'm going to multiply this by 3 cosine t squared and 3 sine t squared, and I get 9 sine squared and a 9 cosine squared added together under the radical. And I am going to save myself a couple of steps here, and I'm going to recognize I can factor out a 9. And when I factor out a 9, I can take the square root of 9, and I'm left with sine squared plus cosine squared under the radical. And I know that sine squared plus cosine squared is equal to 1. So really, I am only left with 2 pi from 0 to pi over 3. And then the 3 that comes out of here from the 9 gets multiplied to that 3. So 3 times 3 is 9. And I'm just left with the sine t dt. So if that didn't make sense, obviously take the steps necessary in the middle for you so that you can figure it out. So I now have 18 pi, and the antiderivative of sine is a negative cosine t. And I'm evaluating that from 0 to pi over 3. And cosine of pi over 3 is negative a half. Well, it's a half, but then multiplied by a negative 1. And then cosine of 0 is 1. Don't forget I'm subtracting, but there's a negative there, so it all becomes a positive 1. So I have 1 minus a half. The half times 18 is 9 pi. So the surface area is 9 pi square units. All right, last question, which does require a little bit of being careful, that I'm probably going to open up Desmos for you here in just a second. Okay, so part of the issue with this one is because we're creating something that is not a circle anymore. This is an ellipse. And when the ellipse graphs, it graphs kind of strange. And also it graphs, like the order it graphs is strange, I should say. But also when we're graphing it, and we're looking for the what's going to rotate, you don't want to rotate the whole entire thing. You only want to rotate the part that is to the right of the y-axis, because I only need half of it, because the other half is going to end up rotated. So let me graph this by hand. So this is going to give you the point when t is 0. When t is 0, x is 1. And when t is 0, y is 0. And when t is pi over 3, pi over 2, x is 0. And when t is pi over 2, y is 3. So I have this point up here like this. And the same thing is going to happen down here. Okay. So this is the worst graph ever. But this is my half of an ellipse that I am then going to rotate this way. So I have to figure out a way to make this make sense as I integrate it. So this actually is negative pi over 2, if you want to think of this, the unit circle going this way. So I can't go from 3 pi over 2 to pi over 2. I am instead going to go from negative pi over 2 to pi over 2. Or if you prefer, you could go from pi over 2 to 3 pi over 2 and work with those values. Okay, so dx dt, I need to take the derivatives, is negative sine of t. And dy dt is equal to 3 cosine of t. And then my integral will be 2 pi. And we're going to go from negative pi over 2 to pi over 2. And again, that's just all as I need, because I'm going to rotate this. This is going to be rotated around the y-axis, so I don't need the other half of the ellipse. And because I'm rotating around the y-axis, that means I need the x value, which is cosine of t. And then I substitute in here this thing squared, so sine squared t. And I substitute this thing squared, so 9 cosine squared t. And here's the other issue with this problem. It's not really an issue, it's just that you can't simplify this nicely and do this by hand. So instead you have to use your calculator or Desmos, which I think I will go ahead and open Desmos for us here. So let me get over to here. Then I can also remind you how to graph parametrics while we're at it. So to graph parametrics, there's a couple of things you can do. I am going to graph just the actual coordinates. So it's going to be cosine of t, comma 3, sine of t. And notice it's just graphing all the points put together. And if I go from 0 to pi over 2, I get that quarter of it, but I need half of it so I can revolve it. So negative pi divided by 2 to pi over 2. So there's the graph that we need. Okay, but I can also use decimals to integrate, right? So I know I need 2 pi out front, and then I want the integral to go from negative pi divided by 2 to pi over 2. And then out front, I'm just going to use x's. It doesn't matter that it's x or t or whatever. Cosine of x, and then I need the square root of sine, it doesn't like it if I'm not careful here, of x squared plus 9 cosine of x squared dx. And that is the correct answer, 30.893. 30.893. And this is totally fine. This is definitely a calculator question. All right, hope that made sense. Make sure you ask questions in class tomorrow if you don't understand.